welcome. So thank you a lot for coming here and being here. So yes, my name is Acebron. I work in Spain, and I have been working for many years now on strong gravitational lensing. So we'll see together what it is, and especially at the scale of galaxy clusters. So these are assembly of groups of galaxies. So let's get started. Yes, okay, so this is the title. So it's fitting that we are in a bar to talk about lensing, because you can use, for those that order some wine, you can use your glass of wine to actually do some lensing. So this is with optics, and we will see that in space it's the same, except that the bending of light is with gravity instead of just the normal lenses that we are used to. So we can play the game of looking at the source light. So in this case it's a candle, and with the bottom of your wine glass, you can put it in between you and the candle. So the candle, we will call it the source, right? And then the glass of wine, we will call it a lens, or also a deflector, since we can see that it's deflecting the light coming from the source. So these are the terms that we commonly use in strong lensing. So you can see that we see different configurations. So first of all, by placing the cup in between us and the candle, we do not really see the candle as it really is, right? So we do not see the source intrinsic position or shape. We see it distorted, so in a different place and with a different shape. So the different shapes that we see will depend on how we tilt this glass of wine. And in the case of real lensing in space, it will be of how massive our cup of glass or a galaxy or galaxy cluster really is. So it depends on where the light rays are going through. So in this case, you can see this is the strong lensing regime. There are different regimes. I will focus on the strong lensing regime because it has the nicest pictures. So here you can see different configurations. So we can see 1, 2, 3, here 1, 2, 3, and then a full ring, right? These are different multiple image configurations. So we call them multiple image because we see multiple times the same image of the same background source, right? So this is why we call it cosmic mirages. These are not real. We just see it because of these mirages in space. So yes, this is just with a glass of wine and traditional optics that maybe some of you may have seen at university, but we see the similar features in space. So for instance, if we look at the full ring, we can see it in space, almost. So this is a very famous lens. So in this case, the lens, remember, that would be the glass of wine. In this case, that is that orange galaxy. Okay, so it's a very massive galaxy, which is between us and a background galaxy, which is this blue, probably spiral galaxy on the background. So that blue galaxy is further away from us than the orange galaxy. So this phenomenon, again, is called strong lensing. So you have the lens and the source. This is at the scale of a single galaxy, right? The deflection is carried out by a single galaxy, but this can happen at larger scales. So for instance, we can go to groups, happy groups. So in this case, you can see different galaxies, and they are belonging together. Let's say they are bound by gravity, and you can easily recognize these galaxies because they have the same colors, okay? They have gone through the same history, and thus they have the same color. This is how you can know when galaxies are probably close together. So in this case, you can see again these orange galaxies, many of them different galaxies, and they are belonging together. Let's say they are bound by gravity, and you can easily recognize these galaxies because they have the same colors, okay? They have gone through the same history, and thus they have the same color. This is how you can know when galaxies are probably close together. So in this case, you can see again these orange galaxies, many of them around in the large field of view, and these are the group of galaxies that is causing the bending of light. And the blue galaxies, here causing the smiley face, these are again further away from us. Okay, so this is not really how they look like, but this is how lensing makes them look like to us. You can see. So larger scales, clusters of galaxies. So this is what I work with. This is one of the most striking ones. It's a very, very massive galaxy cluster. Its name or phone number, it's written there, MAX 04716. And it's one of the galaxy clusters that shows the largest number of multiple images known. So let's say that for a single source, we will have different multiple images, but then we can have various sources, so many sources that are all of them individually lensed, let's say. So we can recognize some, we can play the game of recognizing some by eye, and by the end of the talk you might become lensing experts. So you can see here also some arcs, okay, giant arcs. So these are really distorted multiple images. You can see here one that is mirror. So what else? Again here 1 and 2. Maybe this one, these here 1, 2, 3. So they are easily identified because they have the same color. So meaning that we can identify them by eye that they belong to the same background galaxies because they look very similar. So they must be the same source. Of course, to confirm this, we need to get spectroscopy. This means that we have to get, let's say, a characterization of the spectral energy of that galaxy, and only then we will confirm that it's the same background source. But we can easily recognize them by eye as well. So this is color observation. And this was obtained with the Hubble Space Telescope that you may know of. And then a few years ago, the predecessor, or successor actually, James Webb, imaged the same galaxy cluster. So you can see also the difference between these two and how we are now able to also identify very red objects that were invisible before. So with this new advance, so technological advance by launching a new telescope, we are also able to improve our strong lensing studies. So this means that we are detecting more multiple images, and we can do improved lens models. Okay, so this is just an animation showing you the principle of gravitational lensing, and in fact it's quite an elegant and simple principle. So I already told you, but maybe with the video it's easier. We have a background source that you saw at the beginning, and then the light rays would travel unperturbed to us, right? If there was nothing in between that source and us. However, if there is something in between, let's say a galaxy or a galaxy cluster in my case, then that mass distribution will locally perturb the space-time. Here you can see that it's getting curved. So this local perturbation will make that the light rays that are passing nearby are going to be deflected. Okay? And in particular, in the strong lensing regime, these light rays can take different paths. Okay? There are different solutions to the equation that governs strong lensing. And this means that we can observe actually multiple images of the same background source. Okay? And by looking at these positions and also knowing their distances, we can do cosmology, which I think is pretty cool, but I might be biased. So anyways, this talk has 2 chapters. So chapter 1, cosmology. So I will focus on how we can use these systems to measure how fast the universe is expanding. And chapter 2 will be about lens supernova and how, or supernova, the next supernova, I'll tell you where and when it will explode. So first, why do we care about cosmology and what does cosmology mean? So in cosmology, we are studying the evolution of our universe, okay? And with this, we can do it quite simply, let's say, with a small number of what we call cosmological parameters. So these cosmological parameters, or their values, will then govern how the universe, the history of the universe, how fast it has been expanding, how fast it will expand, so on and so forth, what it is made of. So these parameters are listed there. So first, we see h naught. Okay, so this is telling us how fast the universe is expanding currently. So this is the present cosmic expansion rate. Then we'll have these omega parameters, omega matter and omega lambda, and these are going to tell us the content of the universe. So this is how much matter there is and how much dark energy there is. So by matter, it's total matter, meaning that it's both baryonic, what we are all made of and what we are used to, but also dark matter as well. And then W, which is the dark energy equilibrium state related to dark energy. So in fact, our current knowledge of our universe is based on two mysterious components. So our cosmological model is working to explain the evolution of our universe. It's working very well, but it is based on two components that we know very little of, so dark matter and dark energy. So indeed, one of the challenges of modern cosmology may be to understand better the nature and the properties of these two mysterious components that our cosmological model strongly relies on. So dark matter and dark energy, of course, they are at the moment they are not really observable, but we can study them through their effects on first the formation and evolution of structures. So let's say if we have more matter, there will be more structures, or if there's more dark energy, there will be less structure. So by studying how matter is distributed in the universe, we can tell how much there is of these two quantities. And another way is to measure the expansion and geometry of the universe. And this is typically done by measuring distances. So measuring distances has been a pretty fundamental part of cosmology because it can tell us a lot about our universe, and in particular what I will focus on, which is how fast the universe is expanding. Alright, so now let's see that there are different techniques to do cosmology and to measure the values of these cosmological parameters, and I will focus on one technique, that is strong lensing. So in this case, we'll go slowly. You have two panels, they are the same object. One is a zoom in, and I will show you the differences. So in the first left panel, you can see a lens system, okay? So you have again what we have seen several times. So you have a lens galaxy here in the middle, right? And then you see an almost perfect ring. And if you really look closely, but you can see it better here, there's another structure here, right? It is not so a ring here. So that does mean that there are two sources which are strongly lensed by the same galaxy. Okay? So this is a zoom in, but in this case, the light of the lens, which is here in the middle, has been subtracted just for us to better look at the sources which are strongly lensed. It is still there, this is just for visualization purposes. So you can see that these objects, they are at different distances, okay, from the lens and also from us. So this is measured by what we call redshift. So the lens galaxy in the middle is between us and these different sources, and then this one is nearer to us and this one is further away from us, okay? So then we can use a quantity which is used a lot, and it's one of the fundamental quantities of lensing, which is called the Einstein radius or Einstein angle, and this is telling us mainly the position of that ring, let's say, that we see. Okay. So in this case, we would have two of these values, 2 Einstein radius. We'll see how this is convenient later. So now some equations, but I promise we will go slowly together. So this is just a geometric sketch of what we saw before. So we see first the pretty pictures, and now I get you with some math. But anyway, so you see here the geometric configuration. So we see the observer, that's the eye on the left. Then the red blob, that's the lens. And then you have two blue galaxies, okay, at different distances, which are going to be the sources that are going to be strongly lensed. So in this case, there are different distances that enter into the game. Okay, so the distance between us and the first source, the lens and the first source, and then the lens and the second source, and so on and so forth. Okay, these are shown there in color. So this is one of the fundamental equations of this strong lensing phenomenon. And you can see first alpha, that's the deflection angle. It's telling us how much the light rays are being deflected, okay? And this deflection, so how big this deflection of the light rays is, depends on two terms, okay? You see here first a ratio of these angular diameter or distances, and this is where the cosmology enters, because of course distances in a universe will depend on how it is expanding, what it is made of. So by measuring these distances, we can tell stuff about our universe. And then this complicated term, that's just meaning that this deflection angle also depends on the mass of your lens. So meaning that if your lens is more massive, then the deflection angle will be larger. Okay. This means that for galaxy clusters, the deflection angle are larger than for galaxies in general. Okay. So when we get this, if we measure the deflection angle, we have the mass, and we cannot disentangle the two effects, right? We cannot say whether there is more mass and then this term is smaller, right? We can always find the balance. So we cannot say what is cosmology from what is the mass, let's say. So we need to find the solution. And in that case, there are these systems when we have at least two sources, so two deflection angles, right, as we saw before, that we can measure here. One deflection angle, a second deflection angle. So if we have these two sources, let's say, the length is still the same. This means that if we just take a ratio, this term will cancel out. Okay, this should be taking you back to some courses at uni. But it's just pretty simple. It just means that we find a trick to cancel the dependency on the mass, and then by measuring this ratio of deflection angles for this particular case, we are able to measure this ratio, which is 4 distances. And those 4 distances will depend on cosmology. So we can measure the values of the cosmological parameters. So here you see on the left an image of a galaxy cluster. This is a Bell 1063, and I have color-coded some multiple images. So some are quite easy to see. As you do see, they are similar colors, right? Here, here, here. Also this blue one, and this is quite small. It's very far. So in galaxy clusters, because they are very massive, we can find, in fact, more than 2 sources. So in fact, we can find up to hundreds of sources. So this means that we can do up to 100 minus 1 ratios of deflection angles, as we saw here, right? So in this case, we have many more planes, many more sources. So by doing this, then we can leverage that dependency to get cosmology from this term. And as I mentioned at the beginning, we can measure some of the cosmological parameters. So one is the matter density in our universe, okay, so total, baryonic, and dark. And then the dark energy equation of state, which is relating the pressure and energy density of dark energy. So in this case, you see contours, and this is just the measurements, okay, for given galaxy clusters. So we use more than a single galaxy cluster. We can look at several of them. In this case, the work used 5 galaxy clusters, which are at different distances from us. And each of these contours is a measurement, let's say, on this 2-parameter space, so omega matter and W. And then in black, you see what happens if we combine all the measurements. Of course, if we have the same measurement again and again and again, our precision will increase. So in this case, we are reaching about 10% precision from the combination of only 5 galaxy clusters. And I can tell you that there is about 1 galaxy cluster per square degree of the sky, so there are many, many, many more that can be used for this. And in fact, some of the current and scheduled missions such as Euclid or Rubin, Roman, you might have heard of some, are expected to discover many thousands of these systems. So this is just showing that there is great promise in doing cosmology with these systems. Okay. So I promised that I would tell you how we can use these systems to measure how fast the universe is expanding, and actually with that technique we cannot. But we need a special configuration of lensing, and that happens when the background source is intrinsically variable. It means that its luminosity is varying intrinsically. So this can happen maybe for quasars you might have heard of. So these objects are supermassive black holes at the center of galaxies, which are accreting material, and then their luminosity can stochastically change depending on how much matter they are accreting. So this is why you can see here what we call a light curve, meaning that we will observe night after night after night the same patch of the sky, and we will measure how luminous the 4, let's say in this case 4 quasar images, which are the white blobs there, are every night. And then you get this curve, which is not showing any periodicity, that is just stochastic variations. So one option is quasars, another option would be supernovae. You might have heard of these stellar explosions. So the fact is that we don't know yet how certain types of supernova arise, but we can use how their luminosity varies, meaning that they will brighten and then dim once they disappear, to measure time delays, and I will tell you why. So in fact, in lensing, when we see these 4 multiple images, right, you see again the lens galaxy, this orange galaxy in the middle, and then 4 multiple images of the same background quasar, they will arrive to us at different times, okay? So this is due to the fact that the different multiple images, just as if you're driving your car and you take a different path, you may take longer or shorter to get to work. So these multiple images will take different times to arrive to us. Also, they will go through different gravitational potentials, so different regions of the lens galaxy, so they will be subject to different masses, and therefore they might be slowed down with respect to another, let's say. So there are these 2 effects. So the first thing that we need to do is to measure these relative time delays. So when is one of these multiple images appearing relative to another? So for this, we need in fact these light curves. So in this case, you can see a really nice light curve, and you can recognize by eye patterns, right? The same pattern in the different light curves. So we can just take them, shift them in the x-axis, and then this shift, so in time here, right, it will give us the relative time delay. So when is one appearing compared to another, right? So now again, because I think it's too quiet, some more math. Yes, but we will go slowly. So in fact, this relative time delay that I was telling you about, this delta t, between 2 pairs of multiple images, let's say A and B, will depend again on 2 terms. So, and it's usually the same terms all the time. One will be cosmology, this is why we're here, and another it will be the mass of the lens. So this cosmology term is explained here, and in fact this is proportional to the H0 parameter that we saw at the beginning, which is telling us how fast the universe is currently expanding. So by measuring the two terms, right, we want the purple one, we want the cosmology. So if we measure the time delay on one side and we measure the mass on the other side, then we can get the cosmology. So for time delays, we use long-term photometric monitoring that we have shown here. So here they are over many, many days that we looked at this system. They looked at this system night after night. And then we need to accurately get the mass and precisely get the mass of that lens. So to do that, we need high resolution, so we need space-based imaging of these systems and also spectroscopy, because we need to know the distances of these objects. So when we get these two terms, then the green and the orange, then we can do cosmology. So this is how strong lensing can be used to do cosmology. So both for telling us how fast the universe is evolving, it's expanding, with these particular systems, or also exploiting the fact that we see many multiple images of many background sources to measure the other cosmological parameters. So this idea of using lensed objects or lens quasars or lens supernovae was theorized back in 1964 by Brevstal in what is now a very famous paper, which is very short and sweet, which was with a revolutionary idea. So you can see here that he was saying that the light from a supernova may follow two different paths to the observer, and the difference delta t, so in relative time delay, of the time of light travel for these two paths can amount to a couple of months or more and may be measurable. And this is in fact what happens. However, from 1964 to when we actually managed to get this first measurement done, many years had to pass. Okay? And in fact, it was about 60 years or so until we discovered the first strongly lensed supernova. So this means a supernova that goes off in a given galaxy, and that galaxy happens to be lensed, and then we see multiple images of that supernova. So this is another very famous system. This galaxy cluster, so again, when I say galaxy cluster, you can recognize them by eye because it's just a lot of orange galaxies, okay? So all of those orange galaxies, they are bound by gravity, and they are the galaxy cluster. With, of course, a lot of dark matter that we don't see. But anyways, in this case, so this is MAX 1149, and it's a famous galaxy cluster because it hosts the first strongly lensed supernova, and that supernova happened to go off in this very nice spiral galaxy here. And if you really look closely, you might see the supernova. In fact, there are 4 multiple images already in this image, and there are these 4 knots here. Okay, so these were found back in 2014. And the funny thing is that this spiral galaxy has 3 multiple images. Okay, can you find them? This should be fairly easy. So one here, right? Do you see another multiple image maybe? So it should look similar, right? No?
Bottom right, there's a binary system there. To the
Yes.
right, more to the right.
Right, sorry, I don't know my right and left, as you can see. Around here.
More, even more. To the very edge.
It's not here.
Oh, there's like 3 around that, that's not.
It's not there. So you have one very close by, it's here. It's 1, 2, and you're missing another here, okay? So these are the 3 multiple images of the same background galaxy. This one is the less distorted one, so this is the multiple images that may look closer to what the real source is. So in this case, it's funny because this is a cluster member, right? So a galaxy belonging to the galaxy cluster. And it happens to just fall almost on top of that spiral galaxy, and is strongly lensing again one of the spiral arms of that spiral galaxy. So this is why we see the 4 multiple images of that supernova going off around that galaxy cluster. So these were the first 4 multiple images to be discovered. And then people were using their strong lensing models, so how the modeling the total mass distribution of the system, to predict when and where the next supernova will go off. So of course they have to go off in the multiple images, right? So it can only be here somewhere and here somewhere, right? So they had to look at their models, and their models predicted that this one was the first one to arrive, and it happened actually in the late 1990s. So this was already gone. So they went and had a look at the archive to see if in the images that were taken years ago there was something, but they didn't see anything. So that was a lost cause. However, the interesting thing is that their models were predicted that in 1 year from then, the supernova had to go off somewhere in this galaxy and around this area. Okay. So people worked on improving these strong lensing models to improve the predictions. I will tell you in chapter 2 how the predictions did. But in fact, in spring 2016, you can see the image in there, and you can see the reappearance, which is called SX. So right in this circle. So this system, again, it was used for cosmology because we have a galaxy cluster, so many sources at different redshifts, right? So we can use the first technique that I told you about, but also one source that is intrinsically variable, a supernova. So we can also use the second technique. This means that we can measure all the cosmological parameters in one go, okay? And this is what was done here. So again, I'm showing you measurements, okay? So you can see also with the uncertainties. So you have the histograms here and then the confidence levels, so the measurement within a two-parameter space for the different cosmological parameters. And let's say the more interesting one is H0 here, so how fast the universe is evolving. So these values are in kilometers per second per megaparsec. So how far a galaxy that is 1 megaparsec away from us, which is a lot, is expanding. So this is telling us that it's about 65, 66 kilometers per second, okay, per megaparsec. So this was the first work that managed to measure all of these cosmological parameters with a single system. And in fact, this technique, so this strong lensing in galaxy clusters, is the only technique that allows us to measure simultaneously all of these quantities. Okay, so the idea now is to extend this to other systems, okay, so at the scale of galaxy clusters. So at the moment there are, I would say, few known, although this has been ramping up recently, and I'm showing here a few. So you have the three on the left, these are supernovae that are strongly lensed, and the others, so by galaxy clusters, and the others are quasars, strongly lensed by galaxy clusters. So you can recognize them as whitish blobs here, 1, 2, 3. So in the next part, I will focus on this system, which is a unique system that we call now supernova encore. I'll tell you why. So this is a zoom in. So again, you're seeing here a composite image. So this is obtained with both the Hubble and the James Webb Space Telescope. So again, this is a galaxy cluster, and now you have to be experts at identifying the the galaxies that belong to the cluster. So in this case, they are these whitish galaxies, okay? And then you can see this very nice semi-ring, right, in orange. And then you see also here another multiple image here. This is the same. Okay, so we have, say, 1, 2, 3 here, images of the same background source. So this is further away from us. And that source, that galaxy which is in the background, is special because not only 1, but 2 supernovae went off. So, yes, so the first one is called supernova Requiem, and you can see here these point-like sources. These were discovered in 2016. Unfortunately, they were discovered a posteriori, meaning many years later, because they had a look at the archive and they discovered that these point sources had disappeared, so it must be a supernova. And then more recently, with James Webb imaging, we discovered another supernova. So the first one was called supernova Requiem because we couldn't follow it up. It was not live anymore. And this new one is called supernova on core because it's happening on core on the same source galaxy. So this one, we were lucky enough, we got it live. And this is just showing the multiple images, so you can recognize some as we saw, right? This arc. But then we have also different multiple images at different redshifts together here, color-coded per system. So with this system, we managed to make another measurement of how fast the universe is expanding. So we can focus on this panel here at the bottom, and we have a measurement of 66.9, meaning that a galaxy, again, at 1 megaparsec away from us, would be receding from us at 66.9 kilometers per second. So these are the different measurements that are made in the literature. Ours is the black at the top. The others are also from cluster systems. And this is particularly relevant because there is currently a discrepancy between two techniques, which are very precise because you can see the error bars are very tiny, okay? And this discrepancy, because their errors are very small, is called attention, okay? So all astronomers are worried. And this is why we need alternative techniques to say which one is right, if any of the two, right? So this is how our measurements are comparing at the moment, but of course we need to have more data to improve our measurements and be at some point competitive with these well-established techniques. Okay, so quickly chapter 2, so fantastic meaning lengths, supernovae, and where and when to find them. So I'll told you that astronomers were predicting this multiple image, so supernova to go off in that galaxy, but in fact different teams participated in a challenge, meaning that they were independent teams competing with each other, in fact, to see which one was the best, and not really, but to see which the different predictions and understand how different approaches might impact their predictions. So in this case, you can see the panel that we saw before, right? So you can see the second SX supernova that went off here. Here you have a zoom in. And here you have three teams that got it pretty close together. So the size of the circle is also their error prediction. So you can see that some are smaller than others and some are really at the top. So this means that our knowledge of these systems, how we model the mass distribution of this system, is quite, I would say okay, but I would say it's better than okay, since we got it pretty close, okay? So we really know something about how dark matter and total matter is distributed in these systems. So here you can see a busy plot, but this is the prediction, so the time delay, so when that multiple image would appear, right? So if it's larger, it means we have to wait longer, versus how luminous it would be, okay? So how bright it would be. And then these contours are the measurements, and then the points are the predictions by all the teams, showing that we got it pretty close. So the teams really knew when and where to point the telescope to catch the reappearance, and in fact they did. And the other example, so now I can ask you, do you know, or who knows where the next supernova is going to explode? And the answer is that it's in this system that we saw before, right? So I was telling you there were three multiple images that you can see here that we were seeing in these panels. But actually our models predict that it has to reappear in this year or the next. And that will be in that arc there at the north. So these are the different predictions by the different teams, and you can see that they are pretty close together. So given that the field of view of our telescopes, so either the Hubble or the James Webb, is bigger than this, we will catch it for sure. But we know that it's between 2026 and 2027, and then in this location that the next supernova will go off. So there is at the moment a monitoring campaign, meaning that every month we are observing this galaxy cluster to see if we can catch the reappearance of supernova Requiem. And with this, I thank you for your attention. Thank you.
Thank Thank you, Anna. So we're going to do some question and answers. So please raise your hand, and then I'll call on you. And you're going to bring the microphone? No? Okay. So, yeah.
So you had a graph that showed different predictions for week 0.
Yes. This one. This one.
Right.
The other. Okay.
Yeah. So is it that all of those observations are from the same part of the sky? Can you have different numbers at different parts of the sky?
Right. That's actually a very interesting question. So no, they are different parts of the sky. So each of these measurements, so let's say the colored ones, okay, from the black to the red, they are different systems. So they are labeled, meaning because of course each supernova gets a fancy name. But this is supernova Hope, that's one system. Then Revstar, this is independent work. So that would be the same patch of the sky, and then Encore would be a different region. What was the second follow-up question?
Whether the numbers can be different.
Right. So for the expansion rate of the universe, I don't think so. But one might think to explore the other cosmological grounds, whether there are some anisotropies in the sky. I don't think this is really done. We are just getting the number. But yes, might be something to do maybe in the future when we have more data, more precise data.
Other questions? Yeah. Yeah.
So you mentioned that you are observing once per month to check for the reappearance. So you will get probably like window uncertainty of 1 month, right? You will not be sure when it actually reappeared. So how useful it would be to get better precision in time of reappearance?
Right. So that precision, that cadence of 1 month is at the observer frame, let's say for us. But because of general relativity, there is also this time dilation, let's say. So in the rest frame, which means that at the supernova frame, we would have a higher cadence, so more than a month. Maybe it depends on the distance. So it would be maybe a few days, could be a few days. So we would know when it would explode, let's say within a few days. To improve it, one can think of improving the cadence, but again, because of this time dilation, it might not be so efficient. And then once we observe it, it's not that we use a single measurement. So we build a light curve. So again, what I showed you for the quasars, we do the same for the supernova. And with this, we can better estimate the time delay. So there will be follow-up observations after that reappearance detection to get a more precise measurement. Indeed, from that one, the precision would be smaller, let's say. You're right.
Yeah.
Yeah, maybe it's a bit off topic, but I'm wondering if those lensed supernova light, like a spectrum or something, can be useful for supernova research.
Indeed, yeah. So this is another hot topic, let's say. So especially for type 1a, so we don't really know how the progenitor system, so this is a type of supernova, and we don't know how that explosion occurs. So I think one of the ways to better know is to get very early spectra or observations. And to do that, in fact, we have to know when and where the next supernova will go off. And this is where lensing comes in, because with our predictions, we can really point telescopes to where we think it will happen and get observations very early on. And this is particularly important for supernova physics. Thanks.
Regarding the Hubble postdoc, I was just wondering, is there any chance that maybe it actually shifts over time, that maybe in the early universe and the late universe get actually a bit different?
It is. So this H naught, the 0, it means that it's now. So we are measuring it now. But in fact, if we do it over cosmic history, this is called the Hubble parameter. And it's a value that changes over time. And there are other techniques that can measure this evolution at different ranges. That's right.
Any questions? No other questions?
Yeah,
Okay.
okay. Sort of following on from that, so if you were to do these measurements for like increasingly far objects, could you build something to see how how the difference is over time as you search further back?
Yes, so at the moment there are other techniques that are doing that. So in fact, they can look at objects that are further further away from us, and they can build this function, which is the Hubble parameter versus redshift or time, and measure how this evolves and compare it to our prediction from cosmological models, and by seeing how close we are to that prediction or how off we are, we can see something about our standard cosmological model, if it's correct or not. Indeed, these are the other techniques that can do that.
Sorry, the method you're using is, you said it was large lensing or something? What was it?
Strong lensing?
Strong lensing.
Yeah.
So I'm just wondering, is
Weak lensing?
Yeah.
Indeed,
I'm not
there
exactly
is.
sure what.
There is weak lensing. So in this case, strong lensing, let's say at the scale of galaxy clusters, it happens in the core of this galaxy cluster where the reflection is really, really strong. Weak lensing, naturally, we can think of that it's going on the outskirts of this galaxy cluster when the deflection is smaller. And in fact, this is another technique. We can use it to map the total mass distribution out to large radii. We can also do cosmology and so on, but it's a different technique. I mean, it's similar
Using the same
dependencies.
principle, but
Yes, so strong lensing is non-linear, which makes it beautiful but complicated, let's say. With lensing, there are other complications as well, but yes. So we will not see it by eye, let's say. You cannot see weak lensing by eye. You have to do it statistically. So you have to measure shapes of galaxies and see how, in average, how distorted they are. So, but you cannot see by eye because the effect is very small, very in fact.
thank you.
You have time for one more question? Anyone has one? Yeah.
A sort of follow up to what you're saying, is that the opposite of what happens with a simple lens, where you have more linear effects in the middle, and as you go out, there's more nonlinear effects like chromatic aberration. Whereas in the center you have.
You mean
simple-
like a normal lens?
Normal
Sorry,
lens.
I was thinking.
Yeah.
Yeah.
So is this like the opposite of that? in some way?
I'm not sure I can make now the link to normal optics. This is way back for me. I don't know. I think in this case, so the difference between strong lensing and weak lensing is the total mass distribution. So in this case, it's very dense, very massive, which is causing this large deflection. So we see these spectacular phenomena. When it's smaller, the effect is very small. So the shape of that galaxy would be slightly distorted. So we have to measure many, many shapes of many, many galaxies to get a signal, let's say, an average signal. Yes.
So maybe the difference is whether you're using the force becoming
For weak lensing?
Yeah. Between the strong lensing and the weak lensing. Like strong lensing you might have to go to like higher orders of PPPP and then for weak lensing is some few orders.
So I think it's just all related. So it's just like within the theory of general relativity, the two techniques, I say there are different, but in fact it is just the same theory. It's just that the total mass distribution is different. So we have different effects, and this can expect have different mathematical expressions. Thanks.
Okay, so let's thank Anna again.
Thank you.